Hello everyone, I'm Zhou from Beihang University. Today, I'm going to present our work, Hardware-Aware Graph Neural Network Automated Design for Edge Computing Platforms. This is the outline. The first part is our research motivation. Graph neural networks have been widely applied to various graph-related applications, such as recommendation systems, social network analysis, and molecule property prediction. In addition to these cloud application scenarios, GNN is also becoming popular in many edge applications, such as point cloud processing, image matching, and automatic driving. However, compared with cloud computing platforms, edge devices often have the characteristics of limited resources and low computing power, which poses challenges for GNN to efficiently compute on edge devices. Moreover, gene computing has both characteristics of graph computing and neural network computing, resulting in high computing overhead. For example, a two-layer gene model with only 32 hidden units reaches a peak memory usage of 32 GB on the ready data side, which is intolerable for resource-constrained edge devices. The limited resources on edge devices and huge inference costs lead to low computing efficiency and frequent out-of-memory problems when GNN is deployed on edge devices, limiting their potential to handle real-world edge applications. For example, a popular point cloud processing model, DGCNN, needs more than 4 seconds to handle single-frame point cloud data with 1,024 points on Raspberry Pi, and processing a graph with more than 1,536 points will cause out-of-memory problem during DGCNN inference, which is intolerable for real-time applications. Therefore, how to design efficient GNN models for edge applications is the main issue we want to explore in this work. In order to solve this problem, we obtained 3 observations through experiments and analysis and try to give our solution. Observation 1. Redundant operation brings significant overhead. Generally, GNN design follows the method passing paradigm. Each GNN layer includes some basic operations such as constructing a graph through sampling operation, performing aggregation operation on the graph to complete message propagation, and performing combination operation on all nodes to complete node feature updates. By stacking GNN layers, a complete GNN model is generated. However, this design method will lead to redundant operations in the GNN model and introduce some additional overhead. For example, reusing the results of sampling operation between layers of the DGCNN model does not bring about a significant decrease in accuracy, but greatly improve computation efficiency, which proves the existence of redundant operation in the model design. Therefore, it inspires us to decouple the method passing paradigm by using the fine-grained GNN design space to help reduce redundant operations. Observation 2. Exploring fine-grained design space is costly. Compared with the traditional layer-wide design space, the fine-grained design space no longer stacks GNN layers, but improves the potential of GNN model design by independently selecting specific operations for each position in the model. However, the fine-grained design space will greatly increase the scope of model design exploration. For example, the fine-grained design space covering the DGCNN backbone contains 12 to the power of 3n operations, which n is the number of positions. Such huge design space is difficult to be fully considered by manual design. Fortunately, the automatic method of neural network architecture search provides us a way to explore the huge design space, but such huge search space will lead to a high search cost. Hence, this leads to our second motivation, speed up exploration by search space simplification. Observation 3. The same GNN model may behave differently on various computing platforms. The figure shows the execution time breakdown of DGCNN. It can be seen that Nvidia GPU sampling operation occupy most of the execution time, while on the CPU, aggregation operations are the main bottleneck. Therefore, if you want to design efficient gene model on various edge computing platforms, you need to have hardware awareness when designing the model. This leads to our third motivation: perceive the hardware sensitivities of genes across different computing platforms. At present, there are some manual optimization and automatic design work to try to improve the computational efficiency of gene in edge scenarios, such as model simplification and gene accelerator code search. But this work has some shortcomings. The exciting manual optimization work lacks an effective hardware efficiency perception method, and the optimization effect completely depends on manual experience. The exciting automated design work has achieved good acceleration results, but they basically use estimation-based method to optimize gene efficiency and are only oriented to specific accelerator architecture, so it is difficult to extend to various exciting general purpose edge computing platforms. Therefore, in this work, we want to design efficient gene models for edge computing platforms through an automated method based on hardware awareness and promote the application of gene in actual edge scenarios. Next, I will introduce our proposed graph neural network automated design framework for edge computing platforms, HGNAS. First, in order to generate an efficient gene model on a specific edge devices, the input of HGNAS includes the target device, hardware constraints such as latency requirement, optimization metrics, and specific application. Then HGNAS will enter the design space generation stage to construct a fine-grained operation-based gene design space. After that, HGNAS will enter the design space exploration stage based on the multi-stage exploration strategy and gene hardware performance predictor to quickly construct the optimal gene model that meets the application requirements. This is an overview of HGNAS. To lift the restrictions of the traditional gene design space, instead of presenting the number of gene layers, HGNAS builds the design space upon positions for gene operations to achieve more flexibility. Each position of the gene supernet contains all basic operations such as sampling, aggregation, and possible connection methods such as identity or skip connection. In addition, HGNAS decouples the type and properties of each basic operation and constructs the function space and operation space respectively. The function space includes all specific operation functions such as max aggregator, and all operation types are included in the operation space. The independent function and operation space will also provide support for our proposed multi-stage search strategy, further improving the exploration efficiency. In order to improve the exploration efficiency, HGNAS adopts a multi-stage search strategy. The search process is based on one-shot evolutionary search algorithm. In the first stage, HGNAS performs function search. The goal is to find the site of sighting in the function space to maximize the accuracy of the supernet, which is also to ensure the accuracy of the design model. In the second stage, HGNAS will perform operation search. The goal is to find an operation sighting for each position of the supernet in the operation space, so that the constructed gene model has higher accuracy and lower latency. Specifically, in the function search phase, to further improve the exploration efficiency, HGNAS divide n positions in gene supernet into two halves and share a set of functions among the upper half and another set among the lower half. Afterwards, HGNAS constructs the supernet subarchitecture by uniformly sampling the function space, finds the optimal function space subarchitectures based on the evolutionary algorithm, and then fix the optimal function sightings to the supernet. Fixing function sighting in this stage will significantly reduce the complexity of subsequent operation searches and improve operation search efficiency. During the operational search stage, To improve the search efficiency and meet hardware constraints on the target devices, HGNAS evaluates the candidate architecture based on the proposed hardware performance predictor during the search. Only the architectures that meet the hardware constraints will be further evaluated for the accuracy metric. To meet the efficiency requirement on targeted devices, we built a gene hardware performance predictor that can efficiently learn the relationship between gene architectures and hardware efficiency. We support that gene architectures themselves are also graphs that can be well represented by GNNs. Such a concept is put into good use by drawing on the idea of use GN to perceive GNs. Therefore, HGNAS can effectively perceive the identity of gene candidates through a well-polished gene-based predictor. And HGNAS abstracts gene architecture into dedicated graphs as the input of the gene predictor. The nodes in this architecture graphs represents inputs, outputs, and operations, while the edge represents the data flow within the gene. In addition, HGNAS introduced a global node to improve the graph connectivity and encodes the graph dataset information into the global node to improve prediction accuracy. We use the one-shot encoding strategy to construct the node features. Each node feature vector consists of two parts, operation type and corresponding function. And global node features consist of dataset topological properties like number of nodes. Finally, we build a gene predictor model based on 3 GCN layer and multi-layer perceptron, and trained it by collecting latency information of 30,000 gene architectures on different devices. Since the number of nodes in the gene architecture graph is usually small, so only millisecond level of height is required to complete a prediction. The following are the experimental results. All our experiments are based on the popular PyTorch geometric framework, and taking the average of 10 runs, we select 4 edge devices for actual deployment verification, including Nvidia GPU, Intel CPU, Jetson TX2, and Raspberry Pi. We perform the point cloud classification task based on the modernized 4T dataset and compare it with DGCNN and 2 manual optimization works. As shown in the figure, comparing with manually designed and optimized genes, HGNAS consistently maintains a better performance frontier, higher accuracy, and lower latency on various devices. Compared to all baselines, HGNAS can achieve up to 10.6 times speedup and 88.2% peak memory reduction and 24.9% model size reduction with a negligible accuracy loss on various edge devices. In addition, our gene hardware performance predictor has also achieved high prediction accuracy, more than 80% accuracy across devices with a 10% error bound. And the ablation experiments prove that gene predictor and multi-stage strategy can effectively improve the search efficiency. As we expected, the results clearly show that the hardware-efficient architectures designed by the HGNAS are closely associated with the characteristics of the targeted device, which are consistent with the characterization of gene models in observation 3. For example, the optimal model for Intel CPU has fewer aggregate operations, and models designed for Raspberry Pi tends to simplify each operation. Finally, I will make a summary of our work. In this work, we propose HGNAS, the first hardware-aware framework to explore efficient graph neural network for edge devices. We first achieve hardware performance awareness for genes across edge devices by a gene predictor, and extensive experiments show that HGNAS can design efficient gene models for edge devices within a few hours. That's all for my presentation. Thank you for listening.